Good afternoon, everybody. I'm Adam Smith. I'm a reliability specialist with HECO PSG. This is Jacob Bell. He's also a reliability specialist. He'll be giving you the second part of this presentation. A little bit about myself. I'm an ISO vibration analyst level 3. Before I started into vibration, I originally came from South Carolina. I was in the Marine Corps for 10 years. And while in the service, I did non-destructive inspection, which kind of is how I got into this field. I was getting ready to get out, and I was looking for stuff in this area that kind of pertained to non-destructive inspection, and I found vibration analysis. And I thought it was pretty interesting and stuff, so I was trying to figure out how to get into it. So I found the Vibration Institute, and I called them up. And I talked to this lady named Sue, and she was a real nice lady, and she got me started doing a correspondence course and told me that she could give me somebody that could proctor me in this area whenever I got out. So I did the course and everything, got out, called the guy up. He said, okay, no problem proctoring you, but before we do that, can I take you out in the field and show you what it's like? You know, do some OJT. I said, that'd be great. And he took me out there for a couple hours. We went to lunch, and he said, hey, we want to offer you a job. It was Thomas Patel, you know, Jason's dad, our HECO manager now. And that's pretty much how I got into vibration. I've been doing it for 2.5 years. Okay, this is going to be a basic course about vibration analysis. Our objectives: to understand the basic concept of vibration analysis and how it can be implemented into your facility, how it can benefit your facility, how to select which equipment should be surveyed and how often. If you got any questions or anything, feel free to ask me anytime. Go ahead. Okay, so basic definition of what is vibration. Vibration is mechanical oscillation or motion induced by forces acting on a machine. Repetitive back and forth motion, a motion that repeats itself when it's disturbed from an equilibrium position. So think about a slinky or a spring. If you pull it, it's not going to go exactly back to where it was at. It's going to go past this point of equilibrium and continue to go back and forth as long as the force is there, right? So that's what vibration is. All right, the forces of vibration. Forces can be internal or external. Things like bearing, gear mesh, electrical, these are all internal. Examples: bearings, you know, you have an outer race, an inner race, ball spin, fundamental train frequency. Gear mesh, same thing. You have two gears, they're internal. You got a broken tooth, anything like that, it's a internal force. Electrical, misalignment or something soft foot, you might have an air gap variation that'll cause a electrical signal. External causes: looseness, imbalance, misalignment, rubs. These are all pretty common things. I'm sure you've all heard of them before. Go ahead. Now we're going to get into a little bit of looking at faults and stuff that you can find with vibration analysis. This right here I was not a part of, but it came from a nuclear facility. And the reason for this fault was a lack of lubrication, I believe. You can see the inner race, the outer race, and the ball spin. It was a pretty bad issue because they have damage on all three locations. And this, I'm sure, was found with vibration. This is another good example. This is something I found. This is actually a video, and we do have a few videos that we're going to watch during this. Some of them are pretty funny. This is an example of a dust collector. This is the number 4 or opposite pulley end fan shaft bearing. The damage here was so extreme that you can literally see the shaft moving back inside of it. So it's almost not, it's past the point of bearing wear, and it's almost just an internal looseness issue. And as you can see, you can't really see it now, but you'll see it throughout the video. There's metal flakes all over the top of this pedestal here. That's the metal shavings from inside the bearing. Go ahead and play it though. And you can hear that. We heard this 50 yards away. And we're coming out to this place because they want us to balance these during an outage. And we walk up to this fan, well, we can't balance this one, I'm sorry. They had to replace both the fan shaft bearings and the whole shaft from the run out. But you can see that thing, it's got some serious play in it. I'm sorry, this is a horrible video. I'm not a videographer or anything. But the thing is, we want to catch that before it gets to that point so we can schedule the downtime, not say, hey, thank goodness we see this during an outage, but we're not even here to look at that, but you have a serious problem. And this is the spectrum from that data. Normally, when you have a bearing that has problems or anything like that, it's one of those things we talked about for the internal wear, it would have a non-synchronous pattern and maybe some of this floor noise, but that's only at real high stages of failure. This is all 1 times the fan shaft speed with harmonics and floor noise, so it basically is showing extreme looseness or mechanical looseness. Another common fault we have here is misalignment. You have a parallel misalignment on the top and an angular misalignment on the bottom. And the issue you're going to see, or what you're really going to see, is all these issues, they cause premature bearing failure. Okay, so in this case, if you had a coupling on those, either one, it's going to cause more load on the coupling, which in turn is going to cause load on both shafts and the bearing and cause it to fail. All right, looseness. Looseness can cause vibration in both rotating and non-rotating machinery. Looseness is often due to excessive bearing clearances, loose mounting bolts, mismatched parts, corrosion, and cracked structures. On the left, you have a little example of some excessive clearance inside of a bearing. You can see the rotor rocking back and forth. And on the right is an example of, and this would be internal, and this would be an external. So you got a loose bolt, structural looseness. Tighten up the bolt, and you should correct the problem. This is a video that I found. All these videos I took, except for the one about the bridge. But this one right here is pretty interesting. You can see the gap in between the actual structure and the bolt. I got my hand on the structure, and I didn't know this was here. Okay, I went up and I took readings. I seen what looked like a structural looseness issue in the spectrum. So I did a little investigation. I mean, as soon as I walk up to a machine, I collect 1,000 a day, I don't always go around and hand tight all the bolts, make sure they're good. I look at the data, and if it shows something, then I'll investigate a little further. So I started investigating this one, and go ahead, Bill, and show it. You can see that play. I'm just pushing it with my hand. Probably a 1/2 inch in there. All right, and the reason, that is a concern, but the real concern about that is that fan was hooked to an application that tilted all the way to its side, so it's basically held up by those bolts, so it became a real safety issue too. This is a case of extreme imbalance, and the thing is, I took readings on this motor the month prior. We had some high readings at imbalance. I suggested this thing to be balanced as soon as possible. They did not do it, and this was the result the next month when I went up there. The vibration got so bad that the junction box broke off of the motor. And at the end right here, that's a 40-pound magnet. It literally would walk across the top of it. It's 7 inches per second. So, obviously they didn't fix it at this point. When I showed them this, I said, look, your junction box fell off the side. There is so much vibration. And go to the next picture. So they put a new motor on it. Didn't fix the imbalance at all. They just put a new motor on it. Oh, we got an electrical problem, not a imbalance. The next month I came out, the bolts were shearing off of this motor. The vibration was still so bad. This is an example of a rub. The pulley, somehow the guard got pushed against it. Maybe somebody was working near it, and push it up against the pulley, but you can see the pulley actually rub into the guard there. Really good example of a rub. All kinds of different problems that you see in vibration. All right. Okay, so the definition of vibration analysis. Vibration analysis is the process of finding out what forces correlate with the fault frequencies found in the data plots, either time wave or spectrum. Frequencies such as bearing faults, FFT, cage, BPFO, BPFI, we already talked about all those, gear mesh and blade pass, can be calculated using a few simple algebraic formulas if you have the data needed. In order to calculate gear mesh, you need the internal amount of teeth on each shaft so you can calculate down actual intermediate shaft speeds as well as the gear mesh frequency itself. Blade pass, you need to know how many blades are in there. If you're seeing a high 9 times on a fan and you don't know if there's 9 blades on there or not, you can't really determine if that's a blade pass issue. Bearing frequencies are a little more complicated. You need a lot more information, like you see down here in the key. So say we were going to calculate a ball pass frequency outer race, we would need the number of rolling elements divided by 2 times the machine speed, and then we'd have to go over and get the ball diameter divided by the pitch diameter times the cosine of the contact angle minus 1, and then multiply it back over there. And that would give us our ball pass frequency for the outer race. So we could go into our spectrum after we get that frequency and correlate if there's an issue or if there isn't with that fault.